Okay, we're going to talk about the central limit theorem and a couple of examples. So the central limit theorem tells us about the relationship between the distribution of a random variable and its sampling distribution. Remember, a sampling distribution is obtained by taking samples of, say, size n, finding the mean of that sample. That's an x bar value. Take another sample of size n, find its mean, that's another x bar value. So you keep taking the sample means from your original data set and you get an x bar distribution. So the central limit theorem tells us something about the x bar distribution that results. So let's look at the let part of this theorem. It says if we start with a random variable that is normal and it has a mean of mu and a standard deviation of sigma, and x bar is the sample mean corresponding to random samples of size n, then we have these three things, A, B, and C. The x bar distribution is also normal. B, the mean of the new distribution is the same as the original one. It is still mu. So that the mean of the new distribution, x bar distribution, is the same as your original one. It's still mu. The standard deviation of the x bar distribution is sigma over the square root of n. So we'll call that sigma x bar, and that's going to be sigma over the square root of n. So it depends on the size of your sample. So if your sample gets bigger, the square root of n gets bigger, you're dividing by bigger and bigger numbers, your standard deviation is going to shrink and shrink and shrink. We call this the standard error. So we come up with another distribution, x bar distribution, which is normal, which has the same mean as your original x distribution, and we can define the standard deviation using the original standard deviation of x. Okay. So when we have a normal distribution, the x bar will be normal for any sample size, and we can convert this x bar distribution to the standard normal distribution as we did with just the x. So we were able to turn our x values into z-scores. Similarly here, we use a mean and a standard deviation to get our z-scores. So our z-score is going to be a quotient, x minus mu x bar, sorry, I should say x bar minus mu x bar divided by mu x. So this is very similar to what we usually see. We usually have x minus mu over sigma. So now we are just adjusting this so that we're talking about x bar instead. So we have x bar minus the mu for x bar divided by the sigma for x bar. But given the two equations on the left, it's x bar minus mu, the same one, divided by the standard deviation over radical n. Another way to think of this is, you know that we are dividing by a fraction here, so you could also think x bar minus mu. Divide by a fraction means multiply by the reciprocal. The reciprocal will be square root of n over sigma. So this would be x bar minus mu over sigma times the square root of n. So this is an alternative formulation you can use instead of this if you like. They're equivalent, but this left factor looks very much like this with the adjustment of this square root of n when you're talking about an x bar. So those are the same. Okay. So we can change our x values into z values, so we can use our z table, and now we can also change our x bar values into z values, so we can use our z-table. So let's look at an example here. So we have an X distribution where the mean is 100 and the standard deviation is 48. So we're saying that if we have a random sample of size 81, and we would like to know what's the probability that that random sample is between 92 and 81. So it says to first find the mean and the standard deviation for this distribution. So the mean is the same as our original X distribution. And what about the standard deviation? We have the standard deviation X bar is defined to be the standard deviation of X, our original one, divided by radical n. So we plug in our values of 48 for sigma, 81 for n. The square root of 81, of course, is 9. And we do the division, we get 5.33, approximately. Notice our new standard deviation is much smaller than 48, our original standard deviation. Okay. So now, this is a giant screen with lots of things on it. Let's take it little piece by piece. So what we're looking for is this probability as described right here. We're looking for the value, for the probability that the value of X bar is between 92 and 100. So what we have to do first is to change these X bar values into Z values, which is what we're doing here on this green line. So we know that in the middle, this is the formula that we're going to use. So on the left, we have 92 minus 100 divided by the quotient 48 over square root of 81. On the right, very similar, we have 100 minus 100, so we don't have to do anything further. We notice the numerator is 0, so the whole quotient is 0. So I'd like you to take a second and pause this video, take out your calculator, and see that you do indeed get the same values. Because remember, all of our calculators work slightly differently with respect to the order of operations. Okay, so assuming that you were able to get -1.5 for the Z value, let's continue on. So we changed our X bar values into Z values here. So the probability that we were initially interested in is equivalent to the probability that the Z is between -1.5 and 0. So how do we find the probability that Z is between two values? So let's recall, here's our little normal distribution. Here's 0. Here's -1.5, for example, and we're looking for this probability here. So we're going to find the probability that Z is less than 0, or to the left of 0, and we're going to subtract the probability that it's left of -1.5, that area. So we look these up on our Z table. So the area to the left of Z is 0 is of course a half. Half the area is to the left of the mean. And when we look up -1.50 on our Z table, we get 0.0668. We do the subtraction, the larger minus the smaller, of course, because the resulting area, the resulting probability must be positive, and we get 0.4332. So the central limit theorem's other crucial statement is that even when we do not start with a normal distribution for X, the X bar distribution can look very much like a normal distribution. And in fact, the larger your sample size is, if n is 2, n is 5, n is 15, n is 25, n is 55, n is 100, n is 300, as your sample size gets bigger, the distribution for X bar looks more and more normal. So for us, we're going to consider any sample size of at least 30 that we're going to result in a normal distribution. So let's read through what it actually says here on our slide. If X possesses any distribution with mean mu and standard deviation sigma, then the sample mean X bar based on a random sample of size n will have a distribution that approaches the distribution of a normal random variable with mean mu and standard deviation sigma divided by radical n, as n increases without limit. So it approaches a normal distribution as n increases. So the distribution looks more and more normal as n increases. Okay. So for us, a sample size of at least 30, we're going to assume X bar is approximately normal. Okay, so now you've had a little bit of information about the sampling distribution, the central limit theorem, one example in the central limit theorem, showing how we can change our X bar values into Z values and use the same Z table techniques that we did earlier in the chapter. If you'd like, there is another example of a video using a sampling distribution from Khan Academy, and after you have finished watching that, if you choose to, there's a little 6-question quiz for you to look at that is in Blackboard, so that you can just check to see that you got the main concepts. In class on Monday, we'll go through any questions you might have, and we'll start to look at a worksheet starting with the homework on this material. If you have any questions, you can certainly email me before then, or you can hold on to them for Monday's class.